Hi there. Let's look at electron configuration. Look at the Bohr model of the atom. So we can draw the energy shells, the principal energy levels, the shells 1 to 7, right? And these ones are, I'm cutting from the middle of the atom to the bottom, so I can show you low energy 1, 2, 3, and go on to the higher level of 4, 5, 6, 7. Now, this is showing lowest energy to the highest energy of the energy shells from 1 to the 7. So that's enough to explain almost all the elements 118 that we know of. Now, so also don't forget the number of electrons 288, those things still there, but we want to look at here the subshells. The subshells go from 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, and 7s, right? I mean, we can go on, but this, what is you see here is the principal energy level 1, 2, 3, 4, 5, 6, 7, and the sublevels SPDF, and that's good enough to fill everything in the periodic table. Also, we need to remember S maximum fills is 2, P sublevel maximum is 6, and D sublevel max is 10, and F sublevel max is 14. So that's also important to understand to do the electron configuration, right? So this kind of what I have on the screen now, it's good to have on a piece of paper on your desk. Now the other thing, we're going to start filling from the lowest energy level first, and filling and filling and filling to the higher level of 4, 5, 6, 7, and so on. That is called the Aufbau. Aufbau is actually building up from the scratch. It's a German term, and that means you're building from the bottom, the lower level, to the higher level, and you're filling only the maximum is max. That's, you can't fill beyond that. So S filled into 2, right? And then so this is how you can look at one way. There are a few ways. You fill the lowest level of 1s2, there's nothing else to be filled, you can't go inside the nucleus, so you go backward to the higher level, which is the 2s. Now if you fill the 2s, the max of 2, and then you try to go down again, there's no space, it's all filled. You go back to the higher level, let's 2p, you fill 6, and then you go to the higher level of 3s, you fill 2, there's nothing else to go there, you go backward, and then you keep doing this circle. The diagonal lines, diagonal filling, perfectly indicates from low level of 1 to the higher level of 7, and so on. Now you don't need to do this circle thing that I did. What you can do is you can just draw the diagonal lines like this way. See, 3D 4P 5S, 4D 5P 6S, and 4F 5D 6P 7S. Likewise, you can just draw the diagonal lines, but it's a good habit to do this table like that and have these pictures side by side so you can make sense of side by side learning. Now, so also it's a good idea if you can write this on in a strip of a paper like a ribbon and keep it where you study, right? So that will show you the order of the Aufbau filling order, and then the maximum number of electrons in red. So that's a good idea to have it, right? Now, I mean, for me, I remember these, but it's better to have it on a paper, right? Now, we practice couple of these. Carbon 6, number of protons is 6. You fill 1s2, 2s2, 2p2, from lower to the higher. Then we know 1s2 is helium. That's full shell, and then left over is 2s and 2p. Now the 2s and 2p is the valence shell. I kind of call the V4 engine, because V4 engine is the power that gives the nature of the truck, right? Okay, go to nitrogen 7, you do the same filling, and then you get the helium of the short version, and then 2s2, 2p3 as the V5, valence 5 electrons. Go to 13 aluminum, 1s2, 2s2, 2p6, and 3s2 and 3p1. That'll give me 2, 2, 6, 10, and 13, right? So now 13 is filled aluminum, and then aluminum, this full shell is neon. So you write the short version, which is concise version is neon square bracket, and 3s2, 3p1, which is the valence I call the V3 engine, right? That chemical nature given by the valence 3 electrons. That's why. Now, if you follow this method, you can write almost all 118 elements in this way. No problem at all. You know, you don't need to memorize it. You just follow that method. Now, we can learn few about the monoatomic ions. Anything can have monoatomic ions, any element. That could be chloride minus, potassium plus, oxygen minus 2, and so on. So how do we do that? So the 17 protons minus means add an extra electron, so total of 18 electrons. Let's fill it. 1s2, 2s2, 2p6, 3s2, that's 10, 12, and then we need 5, so that's 17. We need one more, so you're going to make it 6. That'll give me the electron configuration of a full shell, which is the inert gas. Okay, we will get that one. Let's compare with K plus. It's 19, plus means missing an electron. So it's 18 total. Again, you can fill 1s2, 2s2, 2p6, 3s2, 3p6. So they both of them have 18 electrons, right? So if you write the short version, which is argon square bracket, that full shell, just to indicate, and then each version has the chloride, and the K plus has the 18 electrons. So this A and B can be considered as isoelectronic species, and there are many isoelectronic species. Actually, your prof can write them, but if you understand this one or two examples, you are good, right? Okay, so that just to understand that. Now, I'm going to talk about these two. These are special. Chromium 24 and copper 29. So chromium 24, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, right? Yes, because 10, 20, 24. So we need four more. Okay, 24. Now this is what we have been doing for all the time. So we're just going to do the same thing. Let's see what happens. Now copper 29 also, you write that way. So you have 10, 20, then you need 29. So 9 on the 3D. Now these Cr chromium, Cu copper, Cc, I call the C for cancellation. Remember, C for cancellation. Only for chromium and copper this is true. Now we're going to cancel what we wrote, but every other element is fine with this method. So we're going to cancel. What you're going to do, you steal one electron from the 4s, put it into the D. And in both cases, why we do that? Look at this one. 3D has 4. Now we're going to fill one missing hole, right? And then in the copper case, you have 3D9. So 1, 1, 1 at a time, and then you double, 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 one missing, you steal one from 4s and you put it there. Why do we do that? Actually, in nature, it comes with all about energy and the stability. So when you have, let's mark this one here. Yes, when you have, that's argon, and then we had 4s1 3d5. That is the actual way. What we wrote is the cancelled version. Now again in yellow, AR 4s1 3d10. So these are the, on the right are the correct ones. Now we also want to say the half filled D for the chromium and full filled D for the copper stability. Those are the stabilities specially got for chromium and copper to violate the rules that we prepared for all 118 elements. Got it? So C for cancellation, chromium 24, copper 29, steal one from S and put it to the D. Make D5 and D10, which is half filled and full filled stability. Now, here's the good news. Chromium below molybdenum, copper below silver and gold. they will follow the same thing. Of course, little brother, big brother. So it's follow by down the family, right? So that's what we want to know. Now below molybdenum there is tungsten. Don't bother about that. That is a very special metal. It's called the wolfram, and that's a very different metal. Very high melting point, different. Now this is the most common questions the professors would like to ask. The MCAT and other competitive exam, they ask this question because this is important. So ions of ions, that's what I call it. So ion is 26 Fe, and we can write it normally because this is not a cancellation, right? So 1s2, 2s2, 2p6, 10, and then 3s2, 3p6, 4s2, 3d6. So that's 26. It's not a cancellation. It's normally we write. Now, when it comes to Fe2 plus, you remove 2 electrons from the 26. So which one you are going to remove? So let's write the short version. Ar 4s2 3d6. Now Ar 4s2 3d6, the original ion, and then we have to steal or remove, kick out 2 electrons. Which one's going to go? The outermost 4s2, because that's outermost. That's the one going to be removed, right? So therefore you're going to get Ar 4s0 3d6. So that's the nature of Fe2 plus. Now let's compare this one with Fe3 plus. So Fe3 plus 26 electrons originally, 3 plus remove 3 electrons, you end up with 23 electrons, right? So let's put it into the shorter version because you know how to write the, the complete version, right? Extended version, you know. So argon 4s0 and 3d5. Now, because there was 3d6, we can steal 1, and then you get 4s0 3d5. Now look at that one. We can write the short version for the Fe3 plus, and that would be Ar 4s0 3d5. Now look at 3d5. That's 5 electrons perfectly half filled. That's why Fe3 plus is pretty stable, special stability, half filled D. Okay, that's why. Okay, so just a side note here, that's Hund's rule. When you fill one in each cage, and the Hund's in that's dogs basically, Hunts, right? And they eat each other basically. You can't put it in the same cage in a simple way. But that's for a person's name though. But parallel paramagnetic are powerful. That's another thing you can remember. So if the electrons are parallel, they are paramagnetic, they are powerful. Now, see, iron always naturally rust into Fe3 plus. If you want to go back by reduction for iron rust into the pure iron, it's going to cost you because reduction is costly. It's going to cost our pockets. That's why expensive to buy iron and make iron, right? Okie dokie. So we look at a question. So this is a think a question. So tease your brain and see whether you can come up with a good answer. And if not, I will explain. I'll give you hints. These are challenger questions. And look at this pattern. So these are period 1, period 2, period 3. Now, so I'm just going to put this breakdowns a little bit. So it's a good thing to understand this. And what we have is hydrogen and helium. And let's put a little bit more reasonable energy levels. And hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And then you get sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, right? And you can kind of see these pairs. See beryllium to boron, nitrogen to oxygen, and magnesium to aluminum, phosphorus to sulfur. These have the variation of the ionization energy, first ionization energy. That can be explained only using electron configuration. So try to do that. With what we learned in this 10 minutes, you can explain that graph. And it's a valid question. And that's it. The next question is electron configuration using periodic table only, not with this method. Come up with the plan. Thank you.